you've been coming to these meetups regularly, you may know that I share a particular interest in a very specific type of profile pictures. Simply put, they kind of look awesome and they pop out to my eyes when I'm usually doom scrolling on Twitter at midnight. It helps tons that, the people sporting these very particular, very niche profile pictures are usually Web3 contributors, such as Roscoe Callis and Patrick McCory, whom both sport these very niche profile pictures. Our next guest also sports one of these niche profile pictures from a very particular NFT collection. They're called the Bastard Gan Punks. And based on our shared affinity, I trust that my next guest and I will get along just fine because I also really like these NFTs. His name is Louis Guthmann, and he's an ecosystem lead at StarkWare, the organization behind a layer 2 zk rollup called StarkNet. So Louis is currently based in Tel Aviv, Israel, but he studied in France, where he completed a degree in management at the Paris ESSEC Business School. ESSEC. Before moving on to study math, physics, and computer science at a top French graduate engineering school. He has an extensive professional background in data science before joining StarkWare more than 3 years ago as a product manager. He's currently ecosystem lead for the organization. I would say it's probably easy to say that the Web3 bug hit Louis hard at some point because he's also the co-founder of the Zero Knowledge Global Meetup. So this guy, he loves his cryptography and he loves his crypto. So he's also somewhat of a troll because on LinkedIn, I saw you declare in a comment that Web3 is a scam and that's why you're working in it. Just no context. Anyways, there's been tons of announcements on the zero knowledge side of things recently. And if you're unaware, zero knowledge or ZK is another flavor, if you will, for layer 2 scaling. The other, of course, being optimistic rollups. ZK technology is often construed as something of a moon math discipline. But the teams that are working on it are truly working on some revolutionary shit. The team at StarkWare, StarkNet, and Louis, of course, are no exceptions. So without further ado, I'd like to introduce Louis onto the screen.
Wow, what a presentation.
Very impressive. I love doing the intros.
I mean, I have to admit, I feel like on the radio, 99% invisible, and Tim is presenting or something. Congrats. Okay, cool. So yeah, so how are you on the start?
Not sure. Do you have a presentation you want to do, or do you want to just get into a casual chat?
I mean, it really depends on you. So, I mean, I could do a presentation. I think, let me just, it kind of depends sort of how knowledgeable the panel here, the people here are about zk-rollup and zero knowledge proof. So accordingly, I can either put a presentation or simply chat. So it really depends on sort of a quick feedback and feeling of the entire crew here.
Yeah, I don't know. How does everyone feel about ZK stuff? Feel free to unmute your mic or type into the chat box. What's your level of comfort with zero knowledge or?
I worked on the Mina blockchain, which is a zero knowledge based layer 1 called Mina. Oh yeah, the Mina blockchain for a bit. So I would say myself intermediate, but is this in a particular topic, or is this sort of broad zero knowledge rollups?
I have a regular, the startup presentation about sort of how proof brings to scale and what StarkWare is doing, and sort of ecosystem approach, or otherwise, we can just go over question about the space and so on. So let me start with the presentation, a very broad one. I just managed to pull one from a second ago, so let's start with that and let's get going. Here it is. Okay. Here it is. As you can see, so it's actually a quite outdated presentation, I have to admit, December, but should be the trick. Can you see my screen?
I can see your screen.
Yeah, I mean, we'll go over all the ZK EVM, the all of this kind of stuff if you want, and explain the nuance and all of the detail there. But so yeah, so let's start with kind of an overview of Stark zk rollup, Stark Validity Rollup, which is the other name of zk rollup, and kind of understand where we're coming from. So when it comes to blockchain, there is kind of quite a paradox, which is we have a system which are very brand new in some sense, like they just date back 12 years ago, and they are slower than basically any 40 years old system, you know. And the question is, how come? Why? So the reason is because they don't evolve in the same trust model. The trust model of regular, you know, finance and money transfer is what we call delegated accountability, meaning you trust a centralized entity, your bank, or a set of centralized entities, a consortium of banks working with one another. In blockchain, you actually have a very different paradigm. You are what we are looking into inclusive accountability. And so inclusive accountability means there is no this big centralized server. There is you, and you can verify anything that happened on the network. And so because you do that, like you have this much more stronger trust assumption, you are usually in the current form of chains sacrifice privacy and scalability. By scalability, I mean the following thing. Scalability means I'm gonna have less or more transaction for the same hardware. Okay. And so the question is, how do you scale inclusive accountability? As I said, today we have the TradFi, which is centralized entities, very fast, very big machine, connected to each other through business contract. The other one is blockchain, slow, but very optimized in one dimension, which is the trustlessness. And so one is fast and exclusive, the other one is slow and inclusive. And so how do you make chains faster? The simplest solution is say, oh, you know what, just make it bigger, make more block transaction per block. And so the problem when you do that is that you are expelling from the network the smallest actor. So one thing people love to do is to compare the trust assumption of you know, the TPS, number of transactions per second, between Bitcoin and ETH and Solana. And I like to explain that this is nonsensical because we are not comparing the same thing. So one is like comparing an apple to an orange to a Ferrari. And the reason is very simple, is the target machine for the Bitcoin network, the smallest machine in the network that is supposed to follow the network on Bitcoin is a Raspberry Pi. On Ethereum, it's a $2,500 laptop. And on Solana, you can argue that it's a $2,000 machine per month. So, you know, when you're a kid in Uganda, to get a random, you know, example, spinning up a Raspberry Pi is it can be easy. Like it's maybe you can access a Raspberry Pi, maybe you can return on your phone, but basically it's the slowest potential out of computer you're gonna get. And buying an expensive $2,000 laptop is maybe too expensive for you. For the somewhat rich kids in university in various places, I've actually seen a strong laptop is something that is trivial. And so Ethereum is good at trust assumption. And at the same time, you know, when you're Solana, you say, you know what, $2,000 machine is like too restrictive. A business can pay $2,000 a month. And all of those are true. But they are a trade-off between decentralization. Why? Because the smallest the machine requirement, the easiest it is to run the network and the more decentralized it should be. So how do you scale? Can you scale it without doing compromise on decentralization? And so one way to do so is through what we call optimistic rollup, fraud-proof rollup, arbitrum optimism. And so here it is semi-inclusive. Why? Because you can indeed verify on your computer, but you kind of assume that some stronger machine is going to keep up with the network at all given time to challenge any arbitrary fraud. And so it's not completely inclusive because as a small laptop, you might not have the computing power to remain on top of the chain and therefore knowing what the fraud happened at the current step. So this is where the zero knowledge proof and the advanced cryptography kicks in. This moon map that Tim talked about is enables you to remain fast and inclusive. Why? Because those big machines that we discussed here now can no longer be the only one to verify. The generator prove that what they did is correct. And anyone else, even the Raspberry Pi, even smaller than the Raspberry Pi, can verify it efficiently. So this is what StarkNet is zk-sync and Polygon Zero, Polygon Hermes, and all of those are doing. So what are proof? Proof, they are doing are composed of 3 elements. They have a statement. A statement is basically a program. So when I'm sending a transaction, I'm sending a statement that this transaction is valid. I mean, I'm going to verify this transaction to be valid against the consensus rule, against the state, and so on. And then what we call the block producer, the miner, is going to look at the transaction and run it. And so at the end of the block, the miner or the sequencer, depending on how you call it, kind of know what's true. I mean, definitely know what's true in that block. Under zero-knowledge proof is going to generate a proof that the block was correctly prior, the price is prior inflation. It's going to compute it correctly. And the proof, the cool thing about it, that it's super efficient. It means that you get scalability. Why? Because the proof will take roughly a small, what we call a quasi-linear runtime to prove, but the verification is in log n, log square to be specific. So I can verify efficiently in log n roughly the runtime of the computation. So now how does it affect chains? Because before, as you can see here, all the transactions need to be verified one by one. Now I can have a prover show me that the database, the state, moved from 1 to B and send the proof along. And now I can just accept the proof and verify. I set this new state and verify the proof, which is very efficient. So StarkWare has 2 offerings, 2 solutions. One is a SaaS platform called StarkX, which is at this stage used by DYDX, Meetup, Sorare, and Diversify. DYDX, everyone knows about it. But Sorare is not the one that most people know about. And Sorare is probably the most successful game in crypto. Sorare doesn't have any token. They do fantasy football, and they are a highly profitable company just selling NFT card of a soccer player. And StarkNet has been live now for almost a year and enables anyone to run smart contracts and basically develop as if they were on Ethereum. So StarkWare, the company, is like doing very well. We actually think the number is wrong now by 100 mil. So we have a lot of researchers now. The team is 100 people. We are focusing on bringing those proofs to production. And so as of May 2021, oh no, the 2022, now we have $630 billion of trading, over 200 million transactions settled. With the bear market, the TVL kind of dropped, but basically all the rest of those numbers remain true. Now the question is, what about StarkNet? StarkNet right now has a very active community, and I'm very proud of it because it wasn't a clear challenge. It was a clear challenge when you started. StarkNet has probably at this point 1,000 monthly active dev, meaning dev that work every month at least or every week on StarkNet. Roughly 20 or 25 projects that fundraised to be only on StarkNet, and over I think the download of like some of our SDK is reaching 60,000, 70,000. The next step of StarkNet, which we announced 2 weeks ago, was the launch of the token, which will enable us to reach decentralized, the universe stage, which is whenever we will be able, anyone will be able to run prover and sequencers. And so the Starknet ecosystem is growing extremely fast. And the whole point here is to say that if you are a dev and you're joining Web3, or if you're not a just on Web3, you should have a look about what's going on StarkNet because it's very, very exciting. In a very brief note, as a developer, what you get on StarkNet that you don't get anywhere else at this point is 3 things. You get cheap cold data, meaning you can pass data from Oracle or from MicroTree for cheap. You cheap computation, which enable things like force seal, meaning the ability to verify the state of Ethereum only using the block hash and go back in time. And you have account abstraction, meaning all wallets are smart contract wallets, which means that you can have application that will smart contract we can also check, make sure that you don't overspend, that you don't get hacked, that you can replace your key, and so on and so forth. A lot of exciting projects are building on top. We already are, I think, kind of feature complete related to ETH. And as of now, we are focusing on developing more tooling infrastructure, security, and getting more and more dev on board to build furthermore the ecosystem and the network. So we have today 2 full nodes, Juno and Pathfinder. We have consolidation made by Open Zeppelin, a block explorer made by Nevermind, a further formal verification, and a Foundry-like infrastructure to write smart contracts. Basically, anything you want should exist or on the verge of existing on StarkNet. So if you have any question about StarkNet, now I'm available, and we can continue for the more cryptography stuff.
So I had a quick question, and then apologies if I missed this during your presentation. But like you mentioned, the verifiers are pretty fast, right? Which makes sense. Oh, I guess makes sense, right? But the proving portion, from what I've understood, can take drastically longer than that, than a quick sort of like few seconds or so. Yeah, go ahead. The proof creation process, my bad.
Yeah, how long does it take? Yeah.
I've heard on the order of magnitudes of hours, or needing to, at least with like, for example, zk-sync, needing to wait, or not needing to, but like it being economical and cost effective to wait for a few hours prior to creating a proof with like a certain number of transactions. Is that something StarkNet is, I'm sure you guys are thinking about in terms of scalability. Can you speak to like where we're at now, like 2022?
So that's a very good question, which will change a lot in a couple of weeks. As of now, we send proof every 8 hours, meaning that if by the time we sort of like send a transaction, you're roughly going to wait 8 hours to, for instance, withdraw an L1. But you have to remember something. The only sort of true case where you're going to feel the latency is when you withdraw. And the comparison goes compared to optimistic rollup, when the withdrawal would take weeks. I mean, literally a week for the same thing. So we already like order of magnitude faster. But now the interesting point is that in a couple of weeks, we're going to have recursion. And so recursion means that you can make a proof of a proof. And so what it means that you can make proof and batching proof together. So I can make smaller proofs that are faster to prove, but on parallelized computers and prove them together. And so we're targeting now in a couple of, I mean, it could change, but roughly we're targeting 1 hour latency in the near future for going back on L1.
Interesting. Thanks for that.
But now, but of course, like I mean, all of this really depends on the number of transactions, because the savings that you get on the zk-rollup are basically based on batching. The savings are like starting at which point do I get saving compared to running things naively. And so the thing is, it's actually relatively low. Last time I checked was a while ago, it was a very long time ago. But I think last time I checked was you only had to wait it for like another transaction to be worth it to batch in terms of cost and verification time. So yeah, so that's kind of where all of this come from. Now, and to conclude on this, you have to remember that, of course, all kind of bridging that exists today, you know, like through liquidity network and so on, can also work independently. The main advantage of those short proof that seems like long, that they're not that long actually. They're not that long because it means that, for instance, as a liquidity provider, only have to provide liquidity for an hour, not for a week, for an hour before getting back my money back on L1 or on L2, whatever you want to say it back to. So yeah, there was a question about solidity to Cairo. Why do we have our own language? That's a very good question. So ZK do not run on the same computing model than x86 computers, I mean CPUs. ZK, your computers run on bits and bytes, right? The cheapest operation you can do is XOR. In a ZK world, the cheapest operation you can do is a division in the term of proving. So you actually have to mimic XOR to make it look like x86. On the other hand, division is expensive on regular CPUs because it requires a lot more operation. And so you are not running on the same computing environment as a start. So as I said, like for instance, the basic element you have on a regular CPU is bits and bytes. In ZK, you have what we call a field element, which is basically a big UInt. And so that's the first point. Why do you need a different programming language? Because that core point is like very telling about the way things change. Another thing is that a ZK, like ZKP, are about verifying. And therefore, the language is non-deterministic or can be made non-deterministic. For instance, let's say I want to compute x square. No, that's not a good example. I'm going to show you them. I have an array, and I know that this element is inside the array. The runtime to find this element in a regular computer, it would be O of n, right? Like I need to run over the array to find it. I know that this element is in the array. Regardless, I know on average it's O of n. In the ZK rollup, I mean, in the ZKP environment, it's actually O of 1. From the complexity, the perspective of the proof. Why? Because I can just show the element in this is at this index. I'm verifying where it is. I don't have to find it. So from the perspective of the ZK, it's O of 1. It's not O of n. So this is just like a couple of examples where you can get dramatic improvement of performance by playing on the specifics of the language, of the environment you work in. And so we optimize for performance, thinking that we can get backward compatibility as a second thought. That's why we now have warp. And that's also why we are pushing for actually other language to compile to Cairo. So it's not entirely true. We actually, we kind of made a very ballsy move back in the day, because when we started, everyone like crapped over us for having our own language. People said, Solidity is the ultimate language that will ever be made in the universe. Nothing will surpass it. And going after telling, we're going to teach you a new language from scratch was a very hard endeavor. The funny story that it's actually at this point, I think, an advantage. I'm going to tell you why. We get, of course, there is a gain in performance that I told you about before. But actually, the funny story that good dev, the non-copy pasta ones, they actually are okay learning something new, if it's cool. And that's what we have seen. Like, if you look at what project being on StarkNet, I can tell you there is almost none that just are copy pastas of what exists elsewhere. If you look at topology, at Brick, at Edge of Vicar, at Giza Tech, VKX, Zigzag, all of those, just to name a few, right, are things that are very different from anything that exists anywhere else. Because there are people who just show up and say, okay, that crazy random idea that I couldn't do on ETH because, goddamn computation is expensive, and call it, now I can do it. Fossil is something that's been drummed about for years, like this storage proof. It's now like viewed as going to be used by SnapshotX and by Loot and by Dopewar and by a lot of applications looking into how they can leverage the reading the state of another chain as an L2 and L1, etc., directly on StarkNet. So why didn't they make their own language? It's because they made a board. They made, I think, in my opinion, sorry, I'm going to be snarky here. a bad choice. No, because I mean, they made a choice, which was to say be EVM compatible, EVM compatible, to please whatever the Ethereum devs were saying at the time. I mean, I think it's I think the loss in performance doesn't make it worth it. And I think I'd rather work from a clean slate than making something that is like weirdly backward compatible.
In your opinion, is the warp transpiler then worth dealing with, or is it better to just learn how?
I mean, if you can run Cairo, I mean, I'm gonna say, I always say to people, warp is great. Like Greg Vardy is an amazing guy. It's a great tool, etc. The thing is, unless you have unless you're 1 inch, and your product by default has to be cross-chain, because it has to, and you want to maintain one single code base for every place you do, because otherwise it's too complicated. Then I would say, yes, as 1 inch, try warp if it works for you. I mean, if you're trying something brand new, why the fuck would you bother with the existing limitation and think that just doesn't make sense? Because for instance, as I say, StarkNet do not have EOAs. We don't have like private keys per se. We have account, and then the private key is just a signer on top. Then messages value, or all of sort of transaction level operation that exists on ETH doesn't make sense. So if you're using something just that exists today, you're gonna have to make an adaptation, which might be annoying.
Awesome. Anyone else have any questions? Nothing about cryptography, perhaps. I'm way out of my realm here. But
I'd be happy to chat about that. Like, what the various variation of zk-VM, if you want. The Solidity compatibility, EVM compatibility in EVM. What was the last one? Equivalence.
Yeah, I think it's equivalence. Yeah.
Yeah.
Sorry. Just to clarify in my head, is StarkNet EVM compatible then? Like,
so if you consider, so we market it this way, but warp is technically EVM compatibility.
I see.
We don't market it this way because we think it's disingenuous to claim that you will be able to just port instantly, because there are things that just don't make sense. Or the model of StarkNet does not follow exactly EVM. So claiming EVM compatibility would be disingenuous, although you can write Solidity to Cairo using warp. But some operations just do not make sense. Some opcode do not make sense. For instance, block timestamp. We don't have block timestamp. I mean, I don't see any sort of, I mean, zk-VM would say block timestamp makes sense, or block hash. There is an opcode, like a word block hash on Solidity, right? I think. It just doesn't make sense for StarkNet. So EVM compatibility means that your VM is able to read Solidity files. So it doesn't have to be read EVM by code, but basically read Solidity and turn it into your language. So this is what zk-sync and warp are doing. You have EVM compatibility, which is you are able to simulate, I believe I recall, to basically take each opcode and turn it into your own VM. So you work at the opcode level, not at the language level. But you are not running the opcode themselves. You are transferring into a new VM. That's what I understand. That's what zk-EVM by Polygon does, Hermes does, I think. And you have the EVM equivalence, which is actually implementing each opcode as its own circuit, which is what Scroll is doing. So, for instance, if I understand, Scroll would be able, for instance, to prove Ethereum. The zk-VM on Polygon would not be able to prove Ethereum. By proving, if I give you a null block of ETH, Scroll should be able to prove it, I don't think that Polygon can per se, in that sense. And obviously, decasync cannot, definitely, because it's based on solidity. No war.
Quick question. So this is probably for a whole other conversation, but is StarkNet quantum safe?
So
the elliptic cryptography.
So Stark are quantum secure. Elliptic curve cannot be made quantum secure by definition of elliptic curve. I mean, by definition of the Shor algorithm, to be specific, I will invite you. So the reason, okay, quantum security is okay. So computers are, you know, the boogeyman of all cryptography, and there is reason why. The reason is because computers are good at basically three things. I mean, we know that they're good at three things. They're good at finding the shortest path. Like, you know, like if I give you like I think if the sales, you know, the salesman problem, they will find you the actual shortest path. The second thing is they are good at, I forgot, but another algorithm. And the last one is they are good at factorizing prime numbers. So RSA is basically toast whenever we have computing computers. And by a modification of the Shor algorithm, you can also break elliptic curve cryptography. Now, hash function, general purpose hash function like SHA or KCHA are not, I mean, they are heuristic. They are not based on any sort of mathematical assumption. They are not breakable as of today, as far as we know, based on quantum computers. And so Stark are post-quantum secure, probably post-quantum secure, as at least if it exists one hash function that is collision resistance. So if it exists one function that is collision resistant, you can get Starks. But as of now, so today the Starks itself are quantum resistant. That's what we also have a quantum resistant signature called Ziggy Stark. But StarkNet is not, because StarkNet uses elliptical cryptography and the state is maintained using something we call Pedersen hash, which is a hash based on elliptic curve. That's it. A question, a couple of questions. I don't know about people leaving.
Cool, perfect. It's like a lot of like the stuff about elliptic curves like that flies right over my head. So I can't.
No, I mean,
feel like I
it's not
can't
hard,
participate.
Like so I mean, I can explain why. I mean,
Likewise.
do you know why? I mean, I can do like, I don't know, if people are bored, I can go over a tiny bit about cryptography. I basically studied cryptography by myself back in 2017, 2018, and you know, sort of like learned it alone. So back in the day. So you know how RSA work, right? Do you know how RSA? Do you know how RSA work?
RSA.
Yeah.
For the somewhat enough to maybe explain to like a kid.
Right. So RSA work because it's hard. It's assumed to be hard to factor two large prime number. If I give you a number and they are the product of two primes, it's hard to factor them because, I mean, you don't know what the prime number is. If the prime number is big enough, you need to iterate over all numbers to get the prime number, right? And so the problem with RSA, I mean, is why it's no longer used for modern cryptography or try to be avoided is because there is an algorithm that breaks, like, so security of cryptography depends on the number of bits within the system you're using, the crystal system. And RSA model, which is basically I take two large number, which is going to be my public key. Okay, I take two big prime number, I multiply them together, and this is my public key. This model has like factorization of that thing as an algorithm which is solvable in, if I recall correctly, so okay, give you an example. Are you familiar with the birthday paradox? Okay. Birthday paradox has nothing to do with cryptography. Birthday paradox is the following thing. Okay, here it is. Imagine you have 50 people in the same room. No, 100 people in the same room. And you starting out, no, okay. You have 25 people in the same room. What's the likelihood of them having the same, two of them having the same birthday?
I don't know what the number is, but at some particular number, it's 100%, right? I don't know what that number is.
25. So if you have 25 people in the same room, chosen randomly, assuming distribution of a birthday or random, what's the likelihood of them having the same birthday? You say there is 30%. If I'm correct, it's 50%. Yes. You checked it, Daniel? Did you check it? Yeah, 50%. I mean, the 50%, I mean, 35, I need to check, but I think it's 50%. Basically, and if you go to like thing 40, you're already at like 9%. Because if you just put the math of it, you can see that it actually just goes very fast. The more people you put together, the more randomness and the more likely they have to collide, basically. And so what happened is there is, for instance, the likelihood of finding the two hash function, the likelihood of finding two numbers that collide that have the same preimage. I mean, an image that has the same preimage. You basically have the security. Like basically, after half the size of the group sample, you have 50% chance of 99% chance of finding collisions. I mean, okay, I digress. Anyway, it's a long. Okay, okay. It was me trying to be fancy here. I'm going to stop there because it's cool, but it's too complicated for a discussion now.
No, I mean, still appreciate you.
The attempt.
The attempt, yeah.
But basically, there is an algorithm that factor prime numbers, two prime numbers in, if I recall, O of like O of like X, like wait, log. I think it's like basically 4 times faster than like 4 times faster, 2 times faster than the regular the dumb algorithm. It's called the Schnorr algorithm. And so you want to use, because you use some structure of natural numbers, and you want to use elliptic curve operation because they don't have the structure, which makes it safe against that. Anyway, long story short, it's cool, but it's a long story.